Perfect. So I want to introduce Rohan Vernekar, which I think has just finished his PhD. Yes? Yeah. He's a research associate at the University of Edinburgh in the School of Engineering. And his research focus on the simulation of microfluidic devices. And so, please.
Yeah, hi. Can you see my screen?
Yes.
Okay, great. So yeah, thank you for the introduction, and thank you for this opportunity to give a talk at the online conference. My name is Rohan, and I work with Tim in Edinburgh. I'm a postdoc there, and my current work is with making a lattice Boltzmann model for particle growth under flow conditions. Yeah, so this work is part of a larger project called SynBIM, going across 3 different universities, Edinburgh, Sheffield, and Strathclyde. And this project deals with manufacture of silica and magnetite material, nanomaterial, using nature-inspired methods. So SynBIM stands for Synthetic Bio-Inspired Manufacturing. And here with the consortium is trying to understand the formation pathways of these nanomaterials, as well as use nature-inspired processes at the industrial scale so that we can have a larger amount of product with less wastage. The project involves both experiments and simulations. And my role in the project is essentially to do modeling of reactive particle growth in solution at the hydrodynamic scale. Now, the nanomaterials have a lot of applications, such as in drug delivery or imaging. But what is important here is that the nanoproduct has a particular size, shape, and porosity for a given application. So it is important when manufacturing these materials to control these parameters. And hydrodynamics can affect these parameters. So it's important to understand what hydrodynamics does to the synthesis of these products out of solution. So this picture gives a very simple formation pathway for the nanomaterials. You've got a precursor, which is your initial sort of input to your solution. Then those become clusters, which are a few nanometers. Then that becomes a nuclei, which is where we can say, oh, we've got something rigid, solid particle. Then this rigid nucleus grows and becomes your nanomaterial through aggregation or through simple growth. So my role in the project is actually looking from the scale, starting from the nucleus scale to nanomaterial scale. And in this case, we are looking at a single nucleus that grows to become a larger nanomaterial. So what is observed experimentally is that already when you have a flow situation and a no flow situation, for example, when your beaker is stirred or when it's not stirred, you get a different shape of a final product. So these are a few examples of what sort of nanomaterials you can get. And when you have stirring, you get a different product. And when you don't have stirring, you get a completely different product. And this means that hydrodynamics affects particle growth. And it's important, if you want to control that, it's important to understand what happens in this process. And this process, so in order to build a model, this process can be divided into sort of 3 simple physical ingredients. One is your particle, which is your nucleus, starting from your nucleus. One is the flow conditions, and one is the solute species. We've got two-way coupling between particle and flow. So through lift and drag and through no-slip condition. And also between the particle and the solute species, we've got a two-way coupling. So you've got reactive growth of the particle due to surface reaction of the solute at the particle boundaries, and the particle boundaries impose no flux condition on the solute. But we've only got a one-way coupling between the flow and the solute species. Now, this is an assumption, and this assumption comes from the fact that our solution is going to be dilute. And this means that the density and viscosity of the fluid is not going to change due to the concentration. So using this picture, we know that now we have these 4 equations to solve for our model. The first is the Navier-Stokes equation, the standard Navier-Stokes, this incompressible one. The second one is the advection diffusion equation. Now, both of these will be solved in our solver using the standard lattice Boltzmann method with the 2 relaxation time collision operator. For the Navier-Stokes, for solid boundaries, we are going to use interpolated Buziti bounce back. And for the advection diffusion, we are going to go with a simple halfway bounce back scheme. The reaction kinetics at the surface of the particle is assumed to be first order reaction. And this is going to give out how much the particle grows. And the particle motion is going to be simple Newton's law. This is resolved for the particles using the momentum exchange algorithm of Ladd and Iden. Now, these equations give out 3 numbers, 3 dimensionless numbers of importance. The first is the Reynolds number, which is momentum diffusion timescale to momentum advection timescale. Then the Peclet number, which is again the diffusion timescale for the solute to the advection timescale for the solute. And then the Damkohler number, which is the ratio of the reaction rate, the surface reaction rate, to the diffusion rate. So the solver framework is similar to something we've seen in the last 2 days in some of the talks, which is a Eulerian Lagrangian framework. We have a moving particle which is sitting on a fixed Eulerian lattice, and the particle growth is local. So essentially, this is done by ensuring that the amount of solution, the amount of solute that is removed from solution is equal to the amount of mass that's added. Essentially, so the amount of mass removed from solution is balanced locally. Now, one of the major challenges here was that we did not want to go for an expensive remeshing procedure on the Lagrangian mesh. So what we can have when the particle grows is that you can have a situation where after growth on the surface of the particle, you've got a locally varying mesh density for the Lagrangian mesh relative to the Eulerian mesh. And so it becomes important to do some sort of mass spreading. So whenever mass is adsorbed from the solution onto the particle surface, you have to smear it out over the particle surface so as to not cause problems due to the non-uniform mesh density. And so this adds a numerical component to the algorithm, which is an addition to the standard lattice Boltzmann stuff, which just ensures how far you spread your mass after it is adsorbed locally in a lattice cell. Right. So that was all about the solver. Now let me go directly to a simple case, a simulation case, which is a simple sheared suspension. Here we have a Couette cell with moving walls on top and bottom and periodic boundaries on the left and right hand side. We've got 9 cells inside, 9 particles or initial seeds for particle growth in this Couette cell lying in the midplane. All of these are 10 lattice units in diameter, and this leads to a volume fraction of about 3.5. The concentration is uniformly distributed throughout the Couette cell, and we've redefined all our numbers, Peclet, Damkohler, and Reynolds, based on the shear rate and the initial particle diameter. So now in this simulation, what we'll do is, or in this setup, what we'll do is we'll explore simulations at different Peclet and Damkohler numbers over 2 orders of magnitude, and we'll keep the Reynolds number constant. This is justified because in our actually experiments that we want to relate back to, the particles are very small. They are nano scale particles. This means that the Reynolds number is going to be 0. And so it's okay to keep the Reynolds number small here, which is 0.1, still not 0. And after running simulations, what we get is a picture like this. These are a set of 9 simulations. On the x-axis, I'm varying the Peclet number, and on the y-axis, I'm varying the Damkohler number over 2 orders of magnitude, as I said before. And in each of these boxes, I have overlaid the final shapes of the particles after a certain non-dimensional time. after all the solute is consumed. So what we see from this picture already is that if we are in a low Damkohler number regime, which is when the reaction rates are very slow, it doesn't really matter what the Peclet number does, which means that our solution is dominated by what the reaction rate is. And so the growth of the particle is limited by the rate of reaction at the surface of the particle. Again, the interesting bit seems to be happening at Damkohler number 1, where the Peclet number change affects the final shape of the particle. The particle sort of goes from a final shape of a rod-like structure to a circular structure with some sort of intermediate shape in between. And it's interesting to understand why this happens. So in order to see what actually happens when we have this sort of regime change of Peclet numbers, we can go to a simulation for the first case highlighted here. And this is the case. And in this video, what we see is that particles that reach the final shape even before they are rotated by the shear flow. And so this means that the particle shape here is actually determined by their initial configuration and confinement due to other particles rather than the Peclet number coming into play. This is a diffusion-dominated case. So the reactive solute is always available at the particle surface for the particles to grow. And then we go to the next case.
5 minutes. Okay.
All right. Thank you very much. Okay. So the next case is the large Peclet number case. And in this case, we're going to see an advection-dominated case. And the reaction here is limited by the diffusion, and particle rotation ensures that you have isotropic growth of the particle in all directions. All right. And quickly, we'll see a case for, I think I'll skip this one because I wanted to show why there is a variation of the particle size when it grows, when we reduce the Damkohler number. And essentially, this is because you've got an advection-dominated case, again, because the Peclet number is high, but the reaction rate is the limiting factor. So the local positions of the particles tend to matter much more. And so you've got you still got symmetric shapes, you've got circular shapes at the end, but you don't have uniform sizes for the particles. Now, another simple question that we can ask here is to know what happens if we change the initial shape of the particles. And here I've got ellipses with axis ratios of 2 or half with two different orientations. In the first one, the long axis is along the flow direction. In the second one, the long axis is perpendicular to the flow direction. And I've plotted in 2 rows what are the final shapes of these particles when we increase the Peclet number from 0.1 to 1. And in both these cases, the Damkohler number is 1. So we have fast surface reactions. And in both these cases, we see that when the Peclet number is very small, which is when the particle shape is determined by confinement, actually the longitudinal growth along perpendicular to the flow direction is much larger because of the initial configuration. And so in one case, you get a circular shape, and in the other case, you get the rod-like shape. But as we increase the Peclet number, particle rotation leads to sort of isotropic growth. And so you tend to sort of recover the ellipsoidal shape. And I presume that if we go further up, we will also recover the axis ratios, though I do not have the simulations yet to show those things. Right. And this is a final slide of how we can relate this back to the experiments. Here I am measuring suspension viscosity change over non-dimensional time. And we see sort of 3 different groups forming here, which are determined by the Damkohler number. So if the Damkohler number is large, you have a very fast change of the suspension viscosity. The large amount of noise in the system is because I've got a very, very small system size. And so when the particles go close to the walls, they cause a large amount of noise in the measured suspension viscosity. And in this way, we can, I think, relate some of the parameters from experiments, because it might be very hard to measure these sort of dynamic changes at sort of nanoscales. So to conclude, what we see in this very simple simulation is that shear flow tends to lead to isotropic growth. And this is because particle rotation seems to even out the growth in all directions for this system. And also suspension confinement can lead to an isotropic growth. Now, since we are in the nanoscale, or we would like to go to the nanoscale experiments, we want to introduce Brownian motion in the future and also particle aggregation. Because definitely shear flow does not seem to lead to different sorts of shapes. Thank you very much for listening, and I hope I was on time.
Yes. Okay. Thank you. There is time for a short question. If there are no questions, I will proceed. Okay. So I want to introduce you, Francesca.
Yes.
Pelusi.
Good morning.
Which is a young and promising PhD student
I hope so.
Of the group of Mauro Sbragaglia at the University of Rome Tor Vergata. So, please.
Thank you very much for the introduction. So I'm Francesca Pelusi, and I am a PhD student in Rome, in Tor Vergata, and I am working in collaboration with some Roman people, as you can see here. The main topic of this talk is the heat transfer mediated by droplets dispersions. So first of all, I want to show you what is the setup of my work. Here you can see a really Benard cell, that means a fluid, in this case a complex fluid, an emulsion, where here the yellow domain corresponds to the oil bubbles. And when you put the system between two walls, a hot wall and a cold wall, you can trigger the convection into the system. So this is the setup of simulation, and tuning the buoyancy force, you can observe or not the transition from a conductive regime to a convective regime. But in order to show you the heat properties of this emulsion, I need to spend just a few words on the rheology of the system. So first of all, emulsions that are typically composed by micrometric droplets of oil that are dispersed in water are part of a wide class of materials that are called heat stress fluids. Here, as example, I show you the mayonnaise, the magma, the foam of a beer, that are all examples that you can find in your ordinary life. But even if these systems are very, very different one from each other, they have in common the possibility to behave both in an elastic and in a viscous way. In fact, if you look at the rheological curve here that relate the force, the applied force per unit area and the velocity gradient, you can see that if you stress the system below the critical threshold, called heat stress, that typically behaves in an elastic way. Instead, if you apply a stress that overcomes the critical threshold, they typically start to flow. And in this case, the rheological curve, the rheological behavior is well described by the phenomenological law of Herschel-Balke. In this law, there is the heat stress, the threshold here, the plastic viscosity A, and the flux index. Just to clarify the difference between a heat stress fluid and a Newtonian fluid, in the Newtonian case, for example, the water, you have the heat stress equal to 0, the plastic viscosity is equal to the dynamic viscosity of the fluid, and n is equal to 1. So typically n is different from 1. Convection in heat stress fluids has a lot of applications, both from the scientific side, for example, in the study of the magma convection, but also in industrial and technological side. To simulate these emulsions under convection, I used the Lattice Boltzmann method. I will not enter into the detail because I know that you are an expert on this method. So I want to stress only the main aspect that I used to do this kind of analysis. So first of all, I have a bicomponent system. So I need to introduce not only a single probability distribution function f, but I need of two distribution functions. And the second key point is that to simulate the convection, I need to introduce also the information on the temperature field. And to do that, I introduced in the method, so I extended the classical lattice Boltzmann method, including the temperature field, adding this probability distribution function G. The coupling between the two components of the fluid and the temperature is included in the collision term, where I add a term that is proportional to the thermal expansion coefficient, alpha. G is the gravity and the temperature itself. So first of all, I performed a benchmark to test the validity of the algorithm. So the validity was confirmed because looking at the evolution in time of the kinetic energy, we can distinguish the case in which we have a conductive regime, that means that the kinetic energy goes to zero here, or a convective regime where the energy reaches a plateau value. So tuning the buoyancy means the buoyancy force and then the gravity here. I can change the Rayleigh number that characterizes the balance between the buoyancy force and the viscous force of the system. And I obtain the same value of the critical Rayleigh number that in the literature is well known correspond to the transition from a conductive regime to the convective regime. All this benchmark was done for a Newtonian fluid, just to have to be sure about the validity of the method. And after that, I introduced the droplets. Here you can see top panel diluted emulsion. So the packing fraction of the bubbles is quite low. In the second case, the packed emulsion, we have a high concentrated emulsion. So all this work is centered and goes around a systematic comparison between these two systems. That are very different, not only from the packing fraction point of view, but also if you look at the rheology, here there is the flow curve for the dilute case and the packed case. We can see that in this case there is the appearance of the yield stress that miss in the dilute case. To study the heat transfer properties of these emulsions, I look at the Nusselt number that can give us information properly on the heat transfer. Just to clarify, the Nusselt number is equal to 1 when the system is in a conductive regime. When it is in a convective regime, the Nusselt number overcomes the unity. So here the first comparison. I look at the evolution in time of the Nusselt number for 3 different stationary values of the Nusselt number, for the dilute case, but also for the packed case. So the first information that we can learn from this plot is that in the packed case, we have very strong fluctuations for all the Nusselt number tested. And from this plot, burn all the work because we try to understand why in the packed case we have this strong fluctuation and who is the responsible of these fluctuations. The first analysis shows that if you look at the extremes of the fluctuations, the minimum and a maximum, here I took only 2, for example, and if you look at the shear map, you can see that knowing that the dark regions correspond to very low values of the shear rate, so we are in this region in the rheology, and the light regions refers to the high shear rate. We are in this region. We can see that there is a big difference between a minimum and a maximum. And this is because in the minimum, we have the majority percentage of the domain that is below the critical threshold. Okay, so the system is very, very viscous, and it is predominantly elastic. In the other case, when we have a maximum of the heat transfer, we have the majority of the domain that is above the critical threshold. So it is a fluid, and it's easier and, to transfer heat through the media. So from this plot, we can see that during this evolution in time, the system transits in a continuous way from an elastic state to a fluid state. But to characterize in a more quantitative way these fluctuations, we need to introduce not only a parameter that is global, because here I look at all the nodes of the domain, but I need to introduce also a local Nusselt number that is defined looking at the single droplets, with the constraint that if you sum over all the Nusselt number droplets, you can obtain again the global Nusselt number. Looking at the probability distribution function normalized to the standard deviation for this new observable, local observable, we can see a neat difference between the dilute case here, empty circles, and the packed case. So the first result is that the tails are very small in the case of the packed emulsion. Here they reach almost 3 or 4 sigma, the standard deviation. In the packed case, instead, we have tails that reach also 9 or 10 standard deviations. So it is an evidence of the plastic response that is enhanced in the case of the packed emulsion and missing in the dilute case. Another information came if you look only at the packed emulsion and you move through the Nusselt number. Coming from, decreasing the Nusselt number, what you can see is that the tails increase. And it is probably due to the fact that moving from high to low Nusselt number, we are approaching the transition from convection to conduction. But what we observe also that when we have maximum of the heat transfer, that means the global Nusselt number, we observe also regions where the displacement is greater in comparison to the average motion of the bubbles. So we look also at the droplet displacement field here for each droplet, and we computed also the droplet displacement fluctuations, means how much they move in comparison to the average motion, average dynamics of the bubbles. And this, we do this to select the extreme event that gave contribution to the maximum of the heat transfer or to the minimum.
Francesca, sorry, 5 minutes.
Okay, thank you very much. I missed only 2 or 3 slides. Okay, here there is a map of the modulus of the absolute value of this observable, looking at the spatial and temporal correlations. You can see that in the dilute case, we don't have so much correlated regions in space and time, but it's very evident if you look at what happened in the packed case. So this is an evidence about the existence of a correlation, a spatial correlation between the droplets. And this is the last results, that is quantitative results, because show in a very, very evident way how in the case of the dilute case, in the dilute emulsion, if you look at the correlation function of this observable, if you stay at the center of the channel, you move through the walls. You can see that the correlation is almost 0 in the case of the dilute emulsion, and there is a great correlation, spatial correlation, in the case of the concentrated emulsion. And this is the proof of the that the heat transfer, the fluctuation, strong fluctuation, that you have only if the system is very concentrated. And this continuous transition from an elastic and a fluid state are due probably to a finite cooperative length between the droplets. So the droplets are the responsible of these observed strong fluctuations. So to summarize, first of all, I extended my lattice Boltzmann method to include also the the temperature field. And I confirmed the validity looking at the literature and what people know about the homogeneous convection means looking at the simple Newtonian fluid. After that, I included also bubbles in the systems, and I observed strong fluctuations if I increase the concentration of the droplets. And these fluctuations are strictly related to the large displacement of the droplets. And so it was also confirmed by the correlation functions that give us an evidence about this large space correlation between the droplets. So thank you for your attention.
Thank you. Grazie. Okay, it is time for questions.
Sauro is here?
Yes.
Sauro, for you it's a spoiler because in a few days I will send you the update about this work.
I think Sauro should open the microphone if he wants to replay. But question? I have a question. If I
Sure.
have well understood, you have used lattice Boltzmann.
Yes.
With 2 components, but it's not a fluctuating LB. No?
It's not, sorry?
Fluctuating.
Yeah.
Lattice Boltzmann.
Mm-hmm.
You expect that the fluctuation can change the results?
Maybe not. I think that we could investigate it, but I don't expect any change in the results.
Okay. Other question?
Can I ask a question?
Yes, please.
It's a nice talk. So in your simulations, I see that the droplets are not uniform. So some are bigger than others. Can you say what the mechanisms are? Is it just because of your initialization, or do you actually capture the droplets coalescing and then maybe splitting? Can you comment on that?
I shared the video again, so I can show you from the video here. So the initialization of the droplets is done in the way that they are monodisperse, okay? So in the case of dilute emulsion, they are effectively monodisperse. In the second case, because of the buoyancy applied, sometimes happens that we lost some droplets because they merge together. But you can see that when, it's only an initial transition, because after the initial transit, you can see that they reach a more, how can I say, more homogeneous state.
Okay, thank you.
You're welcome.
Another question, sorry.
Yes.
You are using a multi-range approach to suppress the coalitions?
Yeah, we introduce some competing interaction to avoid the coalitions of the droplets in the method, and also obviously phase segregation interaction.
Okay, thanks.
You're welcome.
Okay, I think it's the time of the coffee break.
Okay.
So the session will restart
We have 3 talks, but only 2 speakers, if I understand that correctly.
Yeah.
Giacomo will give 2 presentations. Just a bit of information about Giacomo. Of course, you all know him. He's one of the organizers of this year's DSFD, and I think given that it's going online, it's going very well. I'm pleased that the research experience is actually very good, at least for me. I thought it would be less beneficial in terms of learning something new, but it's going well. At least I think so. Right. Giacomo, you are an associate professor or assistant professor?
Yeah.
Associate professor. Congratulations. Associate professor.
Thanks. It's quite a recent achievement. Thanks.
Okay. And you're at Tor Vergata, right?
Yeah.
in engineering, but also you have a visiting scholarship in Harvard.
Yeah.
Fantastic. The first talk will be about mesoscale modeling of PCM-based energy systems, and I will let you know after 15 minutes.
Okay. Thank you very much, Tim, for this
the recording
nice
has
introduction.
Started. Okay, there you go.
Yes, I started. I am trying to share my screen. I think that you see it. Please confirm me.
Yes, I can see it.
Yes, we can see it.
Okay. So thanks again and good morning to everybody. I will present you today, as the chairman was telling before, these two talks about this brand new topic that we are facing in our research group, enlarge the research group that is my research group at Tor Vergata, and also Professor Succi Saulo, his research group at both IIT and CNR. So the mesoscale modeling of PCM-based energy systems. Just a brief index to tell you what are PCM-based energy systems, because maybe not all of you are familiar with this. We will go through the numerical modeling. We will see the results and discussions of these very preliminary implementations. Then we'll draw some conclusions and have a future outlook for what we plan to do in the near future. So PCM materials are phase change materials. They are being used for thermal energy storage, because in the new economy based on low carbon emissions that you can see here, just a sketch to see that it's almost well known by everybody that pollutant emissions and CO2 emissions have a deep impact on all weather and climate changes that we can experience, and rising also temperature. And the renewable energies are seen as a good substitute and a good integration, maybe at the moment, for the fossil fuels. And the problem with the renewable energies is summarized in this chart that you can see. That is, the demand that we have in our societies of electrical power is usually completely decoupled from the availability of renewable energy sources. And here you see just wind and solar power, the purple and the yellow trends. This chart is referred to Italy, but in all over the world you will have something very similar, in which you see that the energy demand, the orange line, is below the sun availability, energy availability for the hot months of the year in our hemisphere, but in the cold months there is a great lack in the availability of sun power availability. And this chart can be also done not on a year basis, but on a daily basis, and you will see almost the very same trend. That is, when you need a high energy, when you have a high energy demand, that is at the morning and during the evening, sun is not available, of course, or it is very, very available with a very low energy capability, and wind is even more volatile in all senses. So we need a buffer from to conjugate the availability of sun power and the energy demand. And there are many ways of doing this buffer, and we focus on thermal energy storage. That is, we will try to store the energy from the sun in its thermal form and make it available when it can be required from the net. Okay, so thermal energy storage can be divided into thermal and chemical species. We will not focus on chemical, but just on thermal, and thermal can be divided into sensible and latent heat storage. The difference is that the sensible heat sees an increase in the temperature of the a large increase in temperature in order to store thermal energy, while the latent heat systems can store a lot of energy at almost constant temperature. This is the trick, you can say. This is their main characteristic. The phase change materials store energy just through this latent heat storage or release, and they are divided into different kinds: organic, inorganic, and eutectic. And all of them have issues and caveats. Okay, so most of all, they are characterized by the capability of storing a large amount of energy. So they are very interesting from this side. The problem is that they have difficulties in the transient, during the transient of energy storage and release, because they have their characteristic time, response time, and there are some issues related to their reliability in thermal cycles, during thermal cycles. So being a quite new research field, some molecules and some species are well known for their reliability, others not. So in this framework, this is just to give you the panorama and the flavor of this research field that is also new for us, and we have just started to face this research field just before the COVID emergency. We started to implement our numerical method. So we use a two-population approach, one for the fluid part and the other for the thermal part, with two BGK approaches with two different characteristic time. Here we take into account the presence of the effects of the thermal energy storage and release through these three contributions that are the buoyancy force, the latent heat release, and the fluid-solid interactions. These effects are all function of the local phase field. So this approach is a two population with a phase field lattice Boltzmann. Okay, just to be completely plain. Here in the equation of the phase field, we see that we have this term, which is basically a reaction rate, which is the derivation, equal to the derivation in time of the local phase field. So R as this expression, we have taken these equations from this seminal work by Sauro in 2001, a PRL with Dr. Miller and Dr. Mazzutti, in which they proposed this for the first time, this approach for the formation of crystal growth. In this equation, you see that the reaction rate has different terms. F plus and F minus are frequency factors, which are related to the phase change phenomena taking place, and these K are two switch functions that have these proper formulations in which you see that there is the critical temperature at which the phase change takes place. You have this S temperature, which is posed to zero, equal to zero in this very basic approach that we are facing, and it would take into account the possibility of different temperatures for the melting, the starting of the melting and the starting of the solidification. And then you have this T width, which controls the width of the interface of the melting front. In fact, PCMs, as I told you before, are complex molecules, and they are not pure substances, usually, in the technical applications, so they are not characterized by just one single value of the temperature for the melting and solidification for the phase change, but they are characterized by an interval, a temperature interval with a certain width according to the substance, and this complicates the simulation very much, because you have that this leads to the formation of a mashed zone between the liquid and the solid part with different temperature distribution and different physical properties. Okay, we have to address all these issues. So The first benchmark that we faced is the very basic one, is the 1D Stefan problem. You see here, just a sketch, you have a slab of solid material with adiabatic walls up and down, and the left wall is heated, so you impose a constant hot temperature, so higher than the solid material, and the other end of the slab is taken with a constant temperature, which we call T cold, which is also the starting temperature of the solid material. So this is a very basic problem. It's just 1D because you can consider this slab as purely monodimensional, and so you have just basically the Stefan number that governs the dynamics of this melting, and the melting front will advance from left to right on your screen according to the propagation of temperature from the left end of the slab. So we did many, of course, many tests in order to validate our code. We considered another seminal work by the group of Professor Chopard and Huber et others from 2008, and we considered different values of the thermal diffusivity, which reflects on the thermal characteristic time. And you can see here that we have a very good agreement with what we were expecting from the analytical and theoretical and numerical results from the literature. Expect that at very high tau for the thermal part, and also Professor Chopard in his work said that this value was quite high, and this little discrepancy with the theoretical expectations were due to this value of tau. Then we also implemented different kinds of adiabatic boundary conditions, and we saw that for this very basic problem, there were no appreciable differences in using equilibrium, temperature, free sleep, and also no sleep for the temperature, just for the G, so the G population, and we saw that there were no appreciable differences. And this is just a very, very vanilla version of our vanilla step of our validation, and we moved so to the second benchmark, convection, which is a much more complicated environment. Since you see here, it is we have many non-dimensional parameters that govern the dynamics of the melting in this cell. We used as standard in literature a square cell with solid material, entirely filled with solid material at T cold at the beginning. We have adiabatic walls up and down, and we usually impose the same T hot at one side of the square. The simulations are all 2D in these very basic presentations that I show you today. So we have the Stefan number as before, but we have also the Prandtl number with thermal diffusivity and, of course, viscosity. Then we have the Fourier number, which gives you the non-dimensional time together with Stefan. And we have the Rayleigh number, as Francesca said before, the dynamics of this phenomena in which temperature is not at all constant and has a major impact on the system are governed by these non-dimensional numbers in which we see the thermal compressibility, the numerical thermal diffusivity, so on and so forth, and the difference between T liquid and T solid. Sorry for this difference. T solid is T cold and T liquid is T hot, and they are kept constant for the entire, at the boundary for the entire duration of the simulation. For convection, which as I told you before is a much more complex issue, we have different melting regimes characterized by the Prandtl number, which can be lower or higher than 1. And for lower than 1 regimes, we see that the melting is similar to what happens for metals. And for higher Prandtl numbers, that is more than 1. Actually, in literature, it is known that for quite enough large values of Prandtl, that is from actually 3.5 more, the effect of Prandtl number becomes almost negligible. So there is not a great difference in running a simulation with Prandtl 10 or 50, okay? And this field is the one that characterizes the behavior of paraffins and organic molecules, which are of greatest interest for us engineers for thermal energy storage.
5 minutes.
Yes. Thanks. Apart from these Prandtl numbers, we have also low Rayleigh regimes and high Rayleigh regimes, which are give rise to completely different dynamics. So let's see what happens. What we do expect in convection. It is known from literature that we start with a very small time interval in which conduction dominates. Then when the liquid part becomes a little bit larger, we see the starting of a convection movement that provides this nose at the top of our computational cell. This advances and then it shrinks the solid more and more. We, as a quantitative parameter, we monitor the Nusselt number, and you can see that from the literature these expressions are quite ugly, but they have been tested and validated many times in the literature. They are acquired, and you see that we have two expressions for Nusselt for high Prandtl number, very low Prandtl numbers, and an infinite estimation from Nusselt. Actually, one of the most cited papers in the literature had a wrong sign in this. If you have some problems, I can help you in finding the actual expression. And we can see that for very small Prandtl numbers and very small Stefan numbers at the middle way of Rayleigh number, we see that our code quite well for the same theta, the same non-dimensional time, capture the phenomena. That is, at the beginning, the front advances parallel to the hot wall. Then this curvature starts to begin at this Rayleigh number. Actually, we underestimate in this field this curvature, but it is due to the very, very low Prandtl number that we are presenting here. For higher Prandtl number, we compare the temperature field with the one presented by Chopard in his paper in 2008, Chopard and others, and you can see that for larger Prandtl numbers, we have a very, very good agreement with our solver, and I can let you see what happens. You see here in this GIF animation, the convection enlarges the liquid part from top to bottom, and this is the trend of the phase field. So red is liquid, black is solid, and here is the temperature with the formation of this plume, which is, we know it is right. So from a quantitative point of view, in what our approach is different, we can deal with with this formulation, we deal with higher Rayleigh number with great accuracy at the moment. You can see it. Here you see that the dots are our simulations. The lines are the theoretical expectations from the formula that I showed you before. And here with the triangles, the data taken from Chopard and others' work in 2008. You can see that it is true and right that we must have a minimal in the Nusselt. I will discuss this in the next presentation. Then there is a plateau, and then it starts to decrease when the liquid front reaches the right wall of the domain. We capture all these three aspects with an accuracy that we are happy of in this preliminary stage. So, concluding, we had a reliable and fast prediction of melting. Our code is quite fast, even if it has two populations, but the phase field is very, very stable. The results are in line with the theoretical expectations, and we have the possibility of reaching very high Rayleigh number. We are at the moment dealing with simulations with Rayleigh 10 to 7 and 10 to 8, which is the domain of the paraffins, and which is very, very interesting for us engineers for the analysis of the performance of thermal energy storage. So thank you for your kind attention, and if you have any questions, I'm here.
Thank you, Giacomo.
Thanks.
Thank you very much. We have time for one question. Anyone in the audience? If not, I have many questions, but I will ask only one. What I probably most important for me to know is what about the phase change and the related density change? If you go from, of course, you take into account that the density is changing when you heat up the liquid, but what happens if the solid melts? What about the density change of the material during phase change?
Thanks, Tim. This is a very good question, and this is a quite remarkable properties of these materials. Since you are dealing with a solid to liquid, we have a very small, for these molecules, a very small variation in density and in specific volume. It can be quantified in very few percent points, so it is just 2%, okay, below 2%. And this is quite good for us, both from a simulation point of view, which is precious, but also from an implementation point of view, because you can deal with these systems without having the issue of considering the increase in specific volume, which otherwise you must consider when you consider a liquid to volume to vapor phase transition, which is dramatic. Okay, so this is quite good, and it is just reabsorbed by our lattice Boltzmann method, this lattice implementation on this little difference.
Thank you very much. Thank you again.
You're very welcome. You're very welcome. Thank you all.
Okay, let's move on to the next speaker, who is the same speaker.
Oh, yes.
But for those people who just came over from Sala Palma, the second speaker in this session will be Giacomo Falcucci, our organizer of the DSFD conference. And in the second talk, he will talk about lattice Boltzmann for melting and solidification with fluctuating thermal boundary conditions. And again, I will let you know after about 15 minutes.
Thank you very much, Tim, for this second kind presentation, and good morning again. So for those who have just connected, and in this work, I will present you the follow-up of the very and the basic simulations that we have seen in the first one. So we will see what happens when we have fluctuating thermal boundary conditions in the same framework. So this is the index. I will just very briefly go through the numerical modeling just for those who have just joined the session, and we will see the results and discussion and some future outlooks. So as before, there is a decoupling between solar energy availability and demand, and we need the energy storage as a buffer. So energy storage can be electrical in the different forms: mechanical energy, chemical energy, electrochemical, superconducting, cryogenic, or thermal energy storage. We focus just on thermal energy storage, and more specifically in latent heat storage systems based on phase change materials. Okay, why, and this is also related to the kind question that the chairman just told me, why using phase change materials? Because we have the possibility of storing energy at almost constant temperature. These are complex molecules, so the temperature of phase change is not totally constant, but it is it belongs to a narrow interval, and we have a very low increase or decrease according to which phase change you are facing in specific volume and thus density. So why using latent heat instead of sensible heat or chemical energy storage? The pros are highlighted here. We have a great energy density for more than sensible heat storage, so we can use less material, and from an economic point of view is a precious thing. It is easier to work with latent heat materials instead of sensible heat because they are chemically less aggressive, and the solid liquid transition brings only a small density change, as stated before. The problem is that the PCMs, so phase change materials, are characterized by low thermal conductivities or diffusivities, and this is a bottleneck from an operational point of view. And according to the different molecules, there can be some issues related to their thermal stability. Okay, so you do not know a priori how many cycles can you do of melting and solidification and melting with your PCM molecule. As stated before, the numerical method is a plain 2 population lattice Boltzmann with a phase field in which we take into account the effects of melting and solidification with 3 terms in the 2 equations. The buoyancy force, the effects of latent heat release, it is this, I'm sorry, there is a typo, and fluid-solid interaction. The fluid-solid interaction is basically responsible of forbidding the passage of momentum from liquid to solid, which would be unphysical. Okay, this is the evolution of the phase field with the reaction term, which is given by the frequency factors and the switch functions that we have seen before. And for more details, you can refer to the seminal work in PRL by Sauro and co-workers in 2001. We just faced the convection environment in this presentation. So we do not do thermal fluctuations for the solid slab, but just focus the convection, which is complicated because it is a 2-dimensional melting problem governed by many different non-dimensional numbers and with different regimes characterized by completely different dynamics. Okay, so as before, we do expect the formation of a convective cell in the top part of the domain, which will go through towards the cold wall and will shrink down the solid part. We will use the Nusselt expressions that I showed you before for Prandtl numbers larger than 1, much lower than 1, and with the infinite Nusselt prediction. Okay, so the first kind of thermal fluctuations that we have considered are those in space. So we impose a sinusoidal profile at the temperature at the hot wall, so on the left, but we saw that even rising the thermal, this static space fluctuation up to more than 10% of the entire hot wall temperature, we saw no appreciable differences for the different Rileys that we have considered. Okay, so no appreciable difference considering different periods, different amplitudes. And why? Because the thermal capacity of the paraffin, we are mainly facing paraffins in these simulations, absorb this difference in temperature, local difference in temperature, and the melting proceeds basically in the very same way as with static thermal conditions on the left wall. So we decided to turn our attention to thermal fluctuations in time, but the problem is what time? We cannot choose any time without any physical basis, and so we went back to the static Nusselt numbers at different Rayleigh. We know from literature that there are 2 characteristic times that govern the evolution of Nusselt number. That is θ1 and θ2. θ1 is the number, the time interval corresponding to the minimum. The minimum belongs to the threshold between the purely conductive behavior in the very early stages of the melting and triggering the inception of the convective movements. So θ1 is a very important parameter. Then θ2 is the parameter which tells us when the liquid front has reached, in the top part of the domain, has reached the right wall, so the cold wall. We decided to turn our attention to consider θ1 as the governing time for the thermal fluctuations. And we consider so θ1, then also θ1 over 2 and 2 θ1 as different times, and for different time periods, and 1% and 5% as the amplitudes. So I will show you these are very preliminary results, so we have neither had the time to discuss them properly inside our groups. Please, I would like to have your impressions also in your comments, which will be very precious for us. So the effect we consider first this Prandtl equal to 1, high Stefan number, and an average value of the Rayleigh number, so 1.7, 10 to 5. 5% amplitude, θ1/2 the period. You can see that in the very early stages, so for θ equal to 0, 0, 1, we have no appreciable differences between what happens in the static and in the fluctuating case, but some differences rise in the velocity profile. These are the velocity profile along the half of the domain when the velocity magnitude, just velocity magnitude. So here we see that in the velocity magnitude, we see there are two vortexes because when the convection movement starts from the hot wall, you have an upward movement that goes back. So you have two peaks in velocity, which is right, but these two peaks in velocities are different when considering these thermal fluctuations in time. If we go up with Rayleigh, and we use a fairly larger Rayleigh number, we see that these effects are increased. So we see that there is something happening that is just related to this time difference in the thermal condition at the boundary, but consider that you have a very small amplitude of 5% on the average, which is the same as the static case. And so we see that there is an appreciable difference in the velocity distribution, but more, we see that the effects are somewhat amplified for what concerns the Nusselt number. And you can see that the Nusselt number follows the fluctuations that we impose to the temperature, but we have imposed a fluctuation of just 5% of the temperature, and we see that the Nusselt number follows this fluctuation, but with an increased amplitude. And we are still wondering on this. The main actor here is the thermal capacity of the substance and its capacity of releasing thus thermal energy and storing it, but we believe that something here is worth investigation and maybe could turn out something interesting for thermal applications, because we were wondering if there may be some phenomena that could enhance the thermal energy, mainly release. So the negative part, the below the average part, the release of thermal energy in order to increase this, which is a problem of phase change materials. So just concluding, this is a brief presentation with very, very brief, very preliminary results, but the approach that I showed in the previous presentation can provide some interesting results in the presence of these thermal fluctuations in time. Space fluctuations, static fluctuation, but fluctuation in space do not provide any interesting result, no difference. But this amplification that we have just seen in the last slide for the Nusselt number may provide some interesting effects for technical applications in order to try to solve the problem of too low thermal diffusivity and thermal conductivity of these phase change materials. So thanks for your kind attention, and I'm here for your questions.
Thank you, Giacomo. Thank you very much. We have actually 5 minutes for comments and questions. I think for this kind of presentation, it makes more sense to contribute by providing comments rather than clarifying questions. Does anyone have any comments or questions?
Yes, can you hear me?
Yes, please. Sauro?
as Giacomo was pointed out, he mentioned this to me, but we never had a chance to discuss it because he is too busy these days. So my comment is just very half-handed. In general, I mean, there are many situations in statistical physics where just by adding the right amount of noise gives spectacular enhancement of the systematic response. One case in point is the stochastic resonance, which,
yes,
by the way,
this was what I was thinking. Thanks.
Yeah, but the stochastic resonance is a very special system. I mean, you need a bistable system. I don't know whether there's bistability here, and you need an oscillating force, which switches from one state to another. But I think besides stochastic resonance, I wonder whether people have already looked into. I mean, whenever you add noise to a nonlinear system, you must be prepared to surprises. And I don't know. I don't think Luca is in the audience, but I know that, for instance, people use oscillating or maybe noise. I don't know exactly boundary condition to stabilize thermal system. So just to say that maybe there might be some indication already existing in the literature, and the first thing to do is just to look into this literature, because again, I think you can always treat actually the boundary condition as a special form of forcing, and and then you have to see how this forcing is coupling to the nonlinearity. I mean, that's the path.
Okay.
But the effect itself looks interesting indeed. So it's worth being analyzed in some depth.
Because of course we have done all the gradient dependency tests, all the repeatability tests, and the effect is there. It's small. It is small. Maybe because we have chosen theta 1, but the effect is there. So it needs our investigation, our time to see what is behind it.
Anyway, that was very interesting, Giacomo. Thank you.
Thanks very much.
We have more time. We have about 2 more minutes for another question or comment.
I would have a question.
Sorry.
Daniele.
Please.
Oh, Max.
Okay, my one is a quick one, I guess at least. What kind of boundary conditions do you use for the temperature, and have you made sure that it works in a transient way? So not all boundary conditions in Lattice Boltzmann are easily applicable for transient boundary values.
This is a very good question. Thanks very much. For the hot wall, if I do understand well. Okay, so here, well, we have tried different kinds of boundary conditions. We have seen that those imposing the equilibrium temperature here, supposing that here you have the equilibrium, may be quite accurate. We are working on different kinds of implementations. Can you recommend something, for instance?
I can disrecommend the equilibrium boundary condition, especially for transient values, because you reset.
Consider that the dynamics is very low. This theta 1 that I showed you, theta 1 here, corresponds to roughly 14,000 time steps. Okay, so you have these transients that this simulation that you see here to arrive to theta 1, these are simulations in the order of hundreds of thousands of time steps. So you have this. It appears as a fast dynamics, but it is we can say quite slow. So this was the reason why we chose equilibrium, probably because it is not a very fast transient. Okay. But of course, we can surely do better than this.
The problem with the equilibrium is that you cut off the non-equilibrium part every time step you process, and by that you impose a very strange heat flux in the first cell of your domain. And when you're doing a finite difference calculation for the Nusselt number from the left-hand wall into the domain, you will include that strange heat flux that is unphysically imposed by the boundary condition to your domain, and that could be a reason for your amplification of the Nusselt number. It doesn't have to be, but I saw that strange effects for the very first and second cell in the lattice Boltzmann grid next to the boundary. The non-equilibrium parts are ill-defined through improper handling of boundaries.
Okay, we have done the Nusselt number evaluation in different stages close to the different lattice points close to the hot wall, and we see this amplification as well, but we will double check this and make sure that it is not related to the boundary condition, of course. Thanks.
Okay, I think that's a perfect time to wrap up the second presentation. We are nearly on time. Thank you very much, Giacomo, again.
You're very welcome. Thanks you, Tim, for your kind sharing these two sessions. Really, thanks very much.
And I think it's a great outcome for you because you got one physical and one numerical idea to check. And that's why we are attending conferences, of course, to get some feedback.
In fact, I'm very happy for this discussion. Thanks.
Okay. The next speaker of the session is Max Gaedtke, who was also the last person asking a question in the previous talk. Max will probably share his screen very soon. And he is a researcher working
on that.
Okay. Max is a researcher working in Germany at the Karlsruhe Institute of Technology. He is working towards his PhD. And Max has also co-organized a number of OpenLB spring schools where he has taught and talked a lot about Lattice Boltzmann and implementation of Lattice Boltzmann. Max, you seem to be set up. The stage is yours. I'll let you know in about 15 minutes, okay?
Thank you very much. 1 second. I assume you can see my first slide already?
Yes, that works.
Very good. Okay, so let's start right ahead. It's my topic today is total enthalpy-based lattice Boltzmann simulations of melting in paraffin, metal foam composite phase-changing materials. So as Giacomo introduced you to phase-changing materials already, this is an extension to work with the drawbacks of pure phase-changing materials. This is actually a joint work with the group of Professor Ben Mullins from Perth in Australia and me from the Lattice Boltzmann Research Group from the Karlsruhe Institute of Technology in Germany. Luckily, I can go over this in a much quicker way because Giacomo introduced you to that already. So latent heat storages have a very great potential when it comes to buffering cold or heat demand. We store melting or crystallization energy in order to preserve heat or cold for a later use. This is especially useful for applications that work within a small temperature range. In the industry, this would be providing buildings a constant working temperature, if you think of office buildings that are air-conditioned, in making air conditioning more sustainable, putting a buffer inside as well, but also in the process industry, think of reactors or other processes that emit heat or need heat. And in the mobility sector as well, there's great application and need for thermal energy storages. 2 examples for these that you can think of, you have something in your head when thinking of a latent heat storage, would be these pocket warmers. You heat them up with boiling water, they liquefy this gel in there liquefies. And then as soon as you click this little plate in there, the crystallization starts, the material solidifies and emits heat. And this heat is then absorbed by your hands, probably, and it's a nice feeling. The other way around works as well. If you put ice cubes that you have solidified beforehand in your freezer, you put them into your drink and they melt slowly and subtract warmth from your drink, and thus cools your drink. However, both these processes have a very long time range. You might even want that in the case of the pocket warmer, but in a technical environment, you can't live with that. It's taking so long that your demanded heat or cold is not there when you need it. So the thermal conductivity is much too low. How to work with that, or how to prevent that. And our solution is looking into porous metal foams. I've got a little picture here on the bottom right. That's a metal foam. It's made of aluminum oxide in this case. You can make them from other metals and from plastics as well. We're looking into aluminum, especially because it has a very high thermal conductivity, and these foams can be produced with high porosities, up to 99% porosity, and very, very high surface areas. They're used in chemical reactors for their high surface area. But we want to look into how can we put things into the latent heat storage, fill them up with the phase-changing material, and then see how the melting is influenced by the structure. Keep in mind that, for example, paraffin to aluminium has a thermal conductivity ratio of more than 1000. So we introduce a very, very high thermal conductivity into the system by only sacrificing a few percent of the volume, the total volume of the latent heat storage. As the Lattice Boltzmann method is known to be very good at pore scale simulations, so resolving the pore scale, we want to evaluate whether ABM is good for this use case, and it hasn't been done before. However, it's a quite tricky system, and I will show you how we did our first steps towards it. So let's quickly go through the methodology here. The enthalpy-based method for melting flows is just a regular Navier-Stokes equation in equation 1 and 2, plus an advection diffusion equation for the enthalpy, which is the sum of the sensible heat plus the latent heat. Yes, very special about this equation here is that the time derivative is a function of the enthalpy, whereas the convection is a function of the sensible heat and the diffusion is a function of the temperature. So keep that in mind if you go for a Lattice Boltzmann algorithm, because you need to apply some tricks to get this actually solved. And we couple via the Bose-Nash approximation for natural convection. So I don't want to go into detail here. For the velocity and the pressure and density field, we use the partially saturated method. That's a linear combination of two collision operators. The weighting factor is a function of the liquid fraction of FL here. So if it's liquid, we apply the standard BGK collision. And if we have a solid at that cell, we apply a non-equilibrium bounce back procedure. So by that, we have an homogeneous algorithm to apply for the whole domain. A little more interesting is how to get the enthalpy-based advection diffusion equation into the lattice Boltzmann algorithm. And for the BGK equation here in equation 9, a second particle distribution function, the relaxation time is now a function of the local diffusivity, which is a local and spatial derivative. It's a function of the space. To get this special behavior of the enthalpy equation into the lattice Boltzmann algorithm, the group of Huang et al. Proposed to change the equilibrium to equation 10, and this is what we did as well. So for the zero direction, we introduce a collection term, which is the enthalpy, and the other directions are actually the standard equilibrium as a function of the temperature, and by this you get this behavior diffusion by the gradient of the temperature and the time derivative as a function of the enthalpy. The enthalpy is then calculated as the zeroth moment of the distribution function G. From the enthalpy, you can calculate the temperature. And as you've seen in Giacomo's presentation, the temperature, when looking at melting, is actually a piecewise linear function, which is given here in equation 12, with the parameters of the solidus enthalpy and the liquidus enthalpy given by HS and HL. So these are the borders of the solidification range. You can also calculate the liquid fraction from that, again, as a piecewise linear function. Having the liquid fraction, you can calculate all the thermal conductivity, heat capacity, and other thermophysical properties as the density, for example, as well, and the diffusivity as a linear combination using the liquid fraction. When looking at our first results, we saw that the BGK algorithm introduces a lot of diffusion at the interface from liquid to solid material, and Huang et al. Proposed to use an MRT scheme for that. However, their MRT scheme is not trivial to extend to 3D, so we propose a TRT scheme, which is much easier to apply from 2D to 3D. This is standard TRT scheme here in equation 14, 15, and 16. The relaxation time is again a function of the diffusivity for the anti-symmetric parts, and for the symmetric parts we calculate it by defining a magic parameter of 1/4, which we found limits the diffusivity at the boundary, so the non-physical diffusion at the boundary quite effectively. Let's go through some validation cases, and I guess Giacomo showed two very popular validation cases, so I almost have the same slides here. The first problem you look at is the Stefan melting. I think I don't need to explain this again, just very brief. You have a bar of material that melts from the left-hand side to the right-hand side with increasing time. And for the phase interface location, for the temperature, you have analytical solutions as a function of time and the Stefan number, which is given in equation 20. We did a grid study with that, and you can see that almost all our configurations for both BGK and TRT, comparing errors for the liquid fraction as well as the temperature scale at least with first order, if not superlinear. However, there's these circles at the top of this graph here that doesn't seem to scale at all. They have no dependence on the resolution whatsoever. And what this is that's the L infinity norms of the liquid fraction fields. The L infinity norm catches the maximum occurring error in the domain. And what we found out is that this is given by the cell at the interface. So in this analytical solution, there's one cell that is always at the interface that you can see here when you draw plot the liquid fraction over the distance from the left-hand wall. And that one cell, because the analytical solution is a jump function, will always be wrong. Just keep that in mind. For the temperature, it looks quite the same. We hit the analytical solution as well as some high-resolution finite volume methods solution here quite good, if not a little better, actually, than the finite volume method.
5 minutes.
Yeah, thank you. We looked at the relaxation time that we can change, and for BGK, we see a massive dependence of the error for both liquid fraction and temperature of the value of tau. And for our TRT scheme, that is much reduced, and therefore we use the TRT scheme in the following examples. We did the melting of gallium, including natural convection as well. I want to go over that. You saw that in Giacomo's presentation as well. So this is the surface line over time, as well as some comparison with measurements, high-resolution simulations with Lattice Boltzmann of Kumar et al. And the finite volume method of Abishek et al. Here. And we're quite close here again, so we're very happy with how our TRT scheme turns out to provide. So let's come to these hybrid phase-changing materials for the last minutes. And these are two geometries we used. They are algorithmically produced, and with this algorithm, we can tune all parameters that are tunable in the production of these foams. So we can tune the porosity, the surface area, the strut diameter, the pore distribution. There's lots of parameters to look into, and all these parameters have not all of these parameters have been investigated. What's their influence on the melting? So for the next simulations, what we did, what the setup was looking like is we had a hot wall at the top of these domains and a cold wall at the bottom. All the other four sides were periodic. And this is another advantage of generating these structures with an algorithm. The foams are actually periodic on themselves. So what we expect is that the heat transfer now from the hot wall to the bottom goes both ways. Through the PCM that we filled in was actually paraffin, as well as through the metal structure of these foams. And as the metal structure has a much higher conductivity as the paraffin, the temperature will increase of the foam first and in higher depth than that of the melting paraffin, which in consequence means that now the effective surface area that we have for the melting process is much increased. And no, I wanted to go somewhere else first. Sorry. Let's look at meshing these things. So looking at the pore distribution and the porosity, we found that our meshing converges. So the porosity went for the reference value quite well when we used finer resolutions. We didn't see that for the surface area though. Under resolving these structures led to much lower surface area than the reference geometries here in dashed lines, whereas increasing the resolution went to a level that is higher than the reference value. And there's a sweet spot. If there's someone who can explain this and how to cope with that in our simulations, as the surface area is a very important thing to multi-domain heat transfer and melting in general, and specifically in this case here, it is very, I'm curious to know how you cope with these things. What we did is we just used the sweet spot resolution, but that effectively limits us to that one resolution here.
Max, it would be good to wrap up in the next 2 minutes.
Okay. Results. This is the melting front over the time. So the Fourier number is some kind of dimensionless time here for the two geometries. As you can see, the algorithm is able to calculate the very complex surface area, and the multi-domain melting is captured. We compared this to Abishek's results for the same geometries for the total liquid fraction, for example here. And what we got is close agreement, but not too close agreement. You can see at the Fourier number of about 30 that there's a increase in the speed of melting that Abishek found and we didn't. And we think this is due to the lack of resolution in the solid structure. So a summary and outlook. I showed a TOT-based enthalpy method for 2D and 3D that's actually extendable and is totally local, so we don't need any non-local processes here to do the coupling, to do the collision. I showed two validation cases, both with very good accordance to our comparison values, as well as precise simulations for a large domain of values for tau and the Stefan number, and the low interfacial diffusion as well. The present LBM is able to recapture the multi-domain heat transfer in those complex structures. The prediction quality is what I call promising. It's not phenomenal for now, especially because we are not able to recapture the acceleration of melting in the so-called second stage in these hybrid foams. And to be considered next is the representation of the surface area that currently limits the resolution of these simulations to a single value, and how to implement something like the surface area into the method. If someone has an idea and thought on that, I would be very happy. And with that, thank you very much for your attention.
Thank you, Max. In the interest of time, I will not permit any questions for the last presentation. If you are interested in learning more about Max's work, then please get in touch via email, because we will, of course, not be able to have a joint lunch break in person. And with this, I would like to close this session, and let's thank Giacomo and Max again for their very nice presentations. Okay, I see that the numbers have increased considerably over the past minutes, and this means it's plenary time. And let me now introduce our